to the case, I'm gonna basically be explaining one important topic, which is drivers and kernel level, which is map drivers and shellcode. So this is going to last for like 1 hour, because the topic that we're talking about is an introduction to rather driver-based bypasses, so this doesn't really have the in-depth explanation and understanding. However, I have to modify my screen settings. Let's do this and that. Okay. Basically, so I have sent all of you the material for today's webinar. However, basically I'm gonna be sending all of you okay. I'm going to be sending all of you more material after this webinar. That new material is going to include the explanations of things that I have prepared for now. I hope that all of you have actually read that material that I sent. If not, then that's on you. That's not. No, okay. Let's just try this. So this is the English version, but I of course also gave all of you. I also gave all of you. By the way, this is a sample which I have not finished, but this will be finalized for the next webinar. So not next webinar, after this webinar, so you guys will receive everything. It's going to be 4 additional papers, as well as the articles that I can write myself. So, what are kernel level drivers, and why exactly do they pose a threat to Windows systems? I know that because this is rather an extended course webinar, we're going to be speaking of it in more analytical way, so for the screen sharing purposes. So this topic, these topics, okay, I think this one is just over. Although I check, okay. So this will be the analysis of unsigned drivers that are manually mapped into memory. And then we also have the common techniques employed for bypassing. So this webinar is primarily going to be about vulnerable drivers. I'm pretty sure that all of you have at least viewed or seen the vulnerable drivers and DLL injections, as well as driver points proof. Yeah, so I'm sure that all of you at least, or most of you have at least viewed the Ocean's detection for vulnerable drivers. And what you guys have to differentiate is the user mode and the kernel mode drivers. So what this refers to is that the user mode is the executions or operations initiated by the user without elevated permissions. What that means is that without running applications as administrator, yes, exactly, without UAC, without administrator, without elevation permissions, without other conditions. For example, there are multiple execution policies. First execution policy is user mode, so the application just executes. Yes, and I'm gonna get to that very soon. So let me take this as an example. Do I have a system informer? No, I don't. I'm gonna be taking this system informer, and I'm also gonna tell you what exactly I have ChatGPT open, so that you guys will see some magic, basically. So the point here is that every application, so that for the applications, yes, these will be covered in the digital forensics webinar, which comes very soon after this. This month is going to be rather introduction to useful methods like this one. So basically, let's not get sidetracked. Well, you guys can just watch these if you want to, otherwise it's not really that useful or necessary. So, as I said, there are several different elevation or execution permissions and execution policies. First one is run as administrator after user mode, so without administrator. So run as administrator of applications means that the application will forcefully execute as admin. For example, those are applications that have their administrator icons, right? So in this case, this one is a user mode, right? So you just open this without admin. However, everything that has the administrator icon, so the shield of administrators, has the execution policy set to run as administrator. What that means is that no matter how you execute that application, each and every time it will execute with elevated, so administrative privileges. So this means that in the context of System Informer, now System Informer is executed as administrator and it has administrative privileges over system processes. However, we know that the Windows system, the structure of Windows systems, consists of elevated processes, so the system processes that require kernel level access. So that's when the kernel level drivers come into play. So first of all, it has to be noted that the kernel level drivers or kernel level, as you guys would call bypasses, have complete access to the device. Complete access to all the processes, all the applications is higher than administrator. Yes, kernel level is higher than administrator. However, it's also worth noting that there is nothing higher than kernel level. So kernel is the highest elevation permissions that a user can attain on their computer system, because it gives them unrestricted access to the device. Now, if you have to do that, so System Informer in itself comes with the kernel level, kernel mode driver. What this means is that without this kernel level driver, System Informer only has access to administrative processes. So it is limited with access to processes that they require administrative permissions. So without this driver itself, you cannot really initiate any analysis of any process. Now, what is the significance? How to access resources? Now we can access system resources, because now you can also see that plus plus, so it just says that it has elevated permissions. What this also means is that the structure of a kernel, I also have to download, search everything for the purposes of. So what this also means, this also means is that now the driver that allows System Informer to initiate this operation functions as a bridge between Nearsoft product and detect drivers. There's you don't need a Nearsoft program to detect drivers, because I'm going to be explaining this to you. After the webinar, you're going to receive the translated guide of whatever I'm explaining right now too. So don't worry about anything, just for now you have to just watch and listen. So what this means is that there is a third party Windows verified driver that has kernel level access. First rule of thumb, as I would call it, is that Windows doesn't allow unsigned or unverified drivers, right? So drivers especially kernel drivers, to execute on the device or have any access. It automatically blocks it. That's why you see error messages show up every time the newer version of Windows is available, and the System Informer has to basically update the kernel level driver. So think of the kernel. Well, I think I can show you guys the examples. Right. So Do I have it here? I don't think I do. No, I don't have screenshots. Okay, ignore that. So think of kernel level drivers as a bridge between the system and processes, or an application in this case. What this means is that I have explained in the previous webinar, which not many of you attended, that every application or every, let's say, I just do every type of service or a process relies on a specific driver. This is this. There are packages, there are triggers, well, which most of them have, and there are also other different files that it communicates between the system and the kernel of a driver. So that this driver, in our case, this driver doesn't really have kernel permissions because we can freely edit its binary path, do the recovery, check the dependencies, stuff like that. Now, in cases of kernel level drivers, what you would see is that this driver will also have other dependencies, and those dependencies will come from other paths of the device. And they most of them are system files. All of these are drivers. Every file that ends with a .sys, if it is not renamed, is a driver. So this service consists of multiple drivers, and it depends on those drivers. So if some of those drivers, for example, this one or this one, are deleted, this service will be corrupted. So there are also other drivers that rely on this main driver. So this is the main driver for ACPIX. ACPIEX is so this driver itself, system file. And so what you would think of drivers is something that communicates the files, the applications, and the software with hardware. What this means is that if you attain the kernel level access to the system, then you will be able to even modify drivers. And you'd have to, first of all, of course, bypass the driver verification, which we're going to get to right now. And you'd also have to somehow get that driver verified by Windows itself. Is there a way to filter humanities or search for only suspicious drivers in this part? It's not easy. Okay, I'm going to say this right now so that analyzing vulnerable drivers is not easy. However, I'm going to make it as easy as possible for you. And I'm actually going to show you that right now. So we know from theory of computers that every driver is located in the system32 directory. Every Windows driver is located in the system32 drivers folder. And we also know from theory of computers, so this is why theoretical knowledge is very important. We know from the theory of computers, especially of Windows operating systems, that every driver as an extension of .sys. Yes, exactly, this is. There's also other places, like, for example, drivers cache and stuff like that. Like, for example, in this case, we have Windows Defender drivers in a very specific folder. So what you would do here is that you would filter for the sys, so the Windows system. No, it's not proof of ban, because you still have to analyze the driver. So here's what I'm going to explain right now. Most of those drivers that are in Windows System32 and Windows XS and other packages because most of the drivers are also come as packages, like in this case, package cache. But they still retain the same familiarity, which is that all of the folders that those drivers are located in are always called drivers. Okay, they're always called drivers. So driver, whatever. So what you were looking for is a folder without the driver's name. Okay, so this one, for example, has backup. This one is just in system32. This one, though, the rest are all in the drivers folders. As you can see, driver store. Everything here is a driver. The only suspicious thing is the system informer SYS, which means that this driver itself came with a third-party software. We know that because it is not located in system32. It is not located in. Yes, you are looking for red flags, exactly. You are using the knowledge that you have in order to determine which driver is the most suspicious. However, there's also easier ways to determine that. For example, you have to open with. So you have to read the content of a driver. So this one, so that you know the structure of a driver. You guys will notice this familiarity. What's this? And executable. It is an MZ. It has an MZ header, which means that it has a similar header like an executable or a TLO file. Is this what for you if you find this visual? Yes, there are thousands of ways. Because so as I said, you would have to get the driver somehow verified by Windows in order for it to actually run on Windows. There's also another way that the malwares use, which is basically modifying the BIOS settings in order to run unverified drivers, like for example disabling secure boot, and there are other details. We're gonna get to that in the digital forensic source. However, here's a thing, okay? Not many people know this, and I don't really recommend that you guys do that. But I would recommend if you guys use total instead. But you could basically drop files in ChatGPT and ask this to deconstruct the internal structure of this driver and tell me the most suspicious details about it. You have to be logged in for this to actually work, but you get the point. Now let's upload this driver to VirusTotal. We know that this driver is a third-party driver. So this is basically going to analyze the entire file, like it is VirusTotal. ChatGPT does do this, so yeah. I figured that out today. I asked this item, was this one? Which way should I proceed? Write a custom parser. Right, so you can just tell these to do that. Okay. Now we go to the VirusTotal. So the first step, obviously, is to read the structure, so know the structure of a driver. So let's take a legitimate Windows 32 base driver. You'll notice that all of those drivers have this program cannot be run in DOS mode, and it is also an MZ header, so it acts like an executable or a DLL file. The structure of this driver, what you're looking for here, is the contents or strings that are the same for almost every and any driver. In my case, I would use this as a verification. Hex editor will work there, yes. Not only hex editor, but anything that allows you to read the binary of this will work. This also has contents like this. So as you can see here, these are the DLL files, or rather the dependencies of a driver. So you would be rather taking those similarities between the drivers. We're gonna cover this better for a different webinar, but as you can see, this has a lot of, yes, of course, obviously the drivers also exist, but most of them are just, yeah, most of them are easily still detectable. Now, I'm saying this because sometimes people would rename the drivers instead of SYS. They would just rename the extension. But you're going to be looking for, like, for example, known SYS files. So there are no drivers anymore, and UTF-8 content would be this. So supposedly this is supposed to find the drivers that are renamed, but you're better off using a path parser for this because, for obvious reasons. It's going to take a long time otherwise. Now, as you see, ChatGPT basically decompiled and deconstructed this entire thing. You can just continue deconstructing this by asking it, yes, continue, blah, blah. And here you will see the most artifacts, so the callbacks of the application. So those are the functions of the kernel driver. So you can basically take these, import them into the path parser, and you can also just, use those markers. So what exactly that is. So then you go to just file filter. So this is just gonna continue analyzing the file for you. You'll analyze the file. You should have something in your mind while you analyze those applications. Because basically they will tell you more that you need to know. For example, if you already know how exactly one driver looks like, you would have necessary knowledge for better luck next time. In this case, we see that the signature of System Informer has been signed and validified, so it is valid. However, so this is sometimes bypassers will pay Microsoft hardware publisher or something to actually sign this file. If they fake the signature, this will show up here. Okay, so the signature verification will show up here. So how exactly would you tell that it has been, altered or it was fake to be the signature? You would be using these identifiers, for example, the sign tool. You know that it was signed with a sign tool, and these flag with a false signature, especially on a driver, is going to be very suspicious. Because you'll notice one thing that all drivers have in common, and that is that all of them are signed. All of them have to be signed. So if there is a driver that is not signed, you can already know that you are dealing with something suspicious. This is going to work as long as they keep the driver on the device. So here's another thing. If you suspect that a driver is not normal or it came from a separate device, just check the properties of it, check the details of it, and then you'd have to decompile this driver. So learn all about it. So Firestore helps you with that, because it shows you its previous names, shows you the signers, so who exactly signed them. You'd always have to have them signed with Microsoft Windows. Okay, so that's the commonality with drivers. Let's go back to the system informant driver. This is the most suspicious one, right? So you can just go to behavior, you go to full reports, and go to the other analyzers, so the vendors that Versatile offers. Here we'll see a lot of things, so different behavioral analysis, the volatility of the application, and stuff like that. You'd also be able to check for this hash on other databases. So malware databases, if they have uploaded it, or if somebody has uploaded it elsewhere. But this one is just VirusTotal. So there is an analysis of a driver through VirusTotal. The signature check should always be accurate. Now here, there are situations where they are not always accurate because, for example, with system informators, the user that allows execution of unsigned drivers in such cases. Another thing here is that you can utilize Event Viewer to tell if a suspicious driver was loaded. So Hayabusa detects this because Event Viewer detects that. And if it unloads the memory, the same information about the load driver survey, yes. Now here's the thing. The drivers are usually used to erase data that is not primarily or regularly erasable otherwise. So for example, they use kernel level drivers to give applications permissions to delete memory data. So in processes, like for example in CSRSS, you can do that otherwise without a kernel level driver. Now, the way you would tell that usually is through event logs because the drivers are right. So through event logs because the drivers are a very sensitive part of Windows. Yeah, I think it will be. I know when I have this scheduled. Let me see. Oh, this is a timeline, so I think it will be like at the end of the month, I think. But it's still very useful. By the way, another thing, you guys, where is it? What you guys can also do is that you can ask the AI over here to explain something to you about the drivers because I added the research for vulnerable drivers and memory forensics and stuff like that. So, for example, how to detect vulnerable drivers. It is supposed to search the entire book, and this entire GitHub, so this entire thing, and will find the matches that involve the letter or the word driver, and will just return that. So you can use that as well. Although it is free and public, people have no idea how to use it for some reason. What is this? Current transfer shows this is called to do the logs before this should. Yeah. That is because between the docs, only between the docs, yes. For example, it just only gave you the volatility solution, although that's not the only one, because you can also use Yara. And it also gives you the rule sets. For example, this one, I will show that this shellcode includes the vulnerable driver detection of the donut shellcode. However, this is my imitation of it. This Yara rule is supposed to help you detect drivers, so use those calls, right? So these ones. Because these are the this is the structure of a driver. So driver entry, bug check, and the load driver and set value key. So you can use that. So this just redirects you there, especially over here. But that's pretty much about the drivers of that. Another thing that you can do, now let's go back to the VirusTotal analysis. VirusTotal is actually very powerful because, so this tells you a lot of things. The behavior in relations tells you a lot of things. Relations tell you where exactly it came from. So this tells you the entire history of the similarities of it. It also gives you the whole graph summary of the, for example, when you have to log into this, which I recommend that you do. Again, you can do that yourself if you want to. Actually, let me do that. Let me do that for you. No volatility can teach me where to places this custom URL. Yes, I'm gonna. Yes, actually, I can teach you that, but not in this webinar, because different topics, Let me log into this so that I show you exactly what I'm talking about. Okay, let me share my screen now, entire screen, blah blah. Okay, so these gives the relations give you a graph of other executions. This is a very powerful tool. Well, before the graph, let's go to the behavior and community. Community, by the way, gives you other detection vendors. So this is very highly um, recommended because this just gave us a detection rule of this driver. Okay, the detection rule of this is so it also gave us the Aristotle matches of that of those. So right, so there's a lot of information that if you dig through this, you will find detections to any and all applications because there are other reference pages. For example, this one flagged the Thor detections of this driver, and basically you can just go and check them out. So there's also statistics and there's the reports of it. Oh no, this is just me reporting false positives. Okay, so before the comments, go to the behavior and look at these headers. Okay, so we know that this driver is designed for 64-bit Windows systems, operating systems. It's an overlay. It is signed and it is native. So this is it tells you what exactly it means to. So it identifies portable executable linked using the native subsystem. So what this means is that it is using its own subsystem, I believe. So kind of, yes, of course. Yes, you can work on this. There's some foundation you're supposed to know more about the driver. Yes, exactly. Exactly. You can use it for more information. Now let's go through the behavior and I'm gonna explain everything I can. There's a first red flag, which means that the driver is obfuscated. Now let's compare that to default. Now, Windows also has obfuscated drivers. That's not a surprise. Almost every driver has to be obfuscated, otherwise somebody's going to detect it. However, notice the difference between the structure of this driver and this driver. Okay, this is a regular Windows driver. You also have this random driver. Let's just take one of the random drivers. You go to behavior, you barely ever see that the driver is obfuscated. The reason to that is that drivers don't need obfuscation. Because they need Windows approval. So whenever you see an obfuscated, where is it? Was it here? Yeah, so whenever you see the obfuscation of a driver, that is a red flag. No, it's not vulnerable, but it is a third-party driver, so not Windows, not a Windows driver. Now, here's the thing. Then you have the Mitre tactics and techniques. By the way, if you guys had no idea, you can also download the artifact examples. So, for example, the JSON of Mitre attacks, and you can also download. Yeah, let's just download the JSON, and yeah, so you can also just check all of those yourself. Yeah, you can just right click on the Mitre tact or click on Mitre tactics, and it's gonna take you to that page. So we have several techniques. The execution, So how exactly does this driver execute itself? This gave you the API call that it uses. So it images, so it accesses the header, so the portable executable header. Now this doesn't tell you much. However, this tells you that there is a mitra technique which is named as shared modules, and here is a definition of it. So right, if you click on view on mitra, yes, yes, we are analyzing the third-party driver. You know that it's a third party. So if you click on the view on mitra, you can also read it here, but I recommend that you always click on view on mitra. Because right now, this explains to you how exactly this shared module technique works and gives you examples of where they were used in other sources, and it also gives you the references. For example, let's click on the first link, it's gonna be the review of it. And this explains to you how exactly what are DLL files, for example. So you basically get free cybersecurity and malware analysis lessons, articles, blog posts by just following the information that you see on your device. For example, you can also just click on this and it's going to take you in the page where that is relevant. So this just basically explains to you how a DLL file works and how exactly they are comprised. Simple stuff in this case. Right, so that's all about this part. And there's also the tactic parents and subsections. So for example, shared modules is a sub-technique of execution techniques. So if you click on execution, you're gonna see all the types of techniques for execution. For example, let's just do, as we said, you also see the known techniques like scheduled tasks for executions, the injections. I also saw auto-hotkey even, and also saw JavaScript, Python, and PowerShell. Alright, PowerShell. So you just go down and find something you want, like malicious link. Click on that, and this is gonna show you, give you an example. So this gives you an example, and this also gives you another example, which is another phishing technique that gives you other references that you can basically click and read yourself. Okay, so that these are the advantages of actually, yeah, yes, of course, yeah. Those are the identified techniques, but I also saw some on 2023 techniques. Now, if that's how you know what you're talking about, basically, you just click on those. Then with the privilege escalation, this tells you that it attaches to the processes, right? So it injects. So this driver injects system informer into all of the processes, and that's how it overtakes the processes. Okay, that's why, for example, if we open this device, go to memory, and we type system. Yes, exactly. You know where to look for those. So this is going to have the DLLs that also comprise system informer. Although not exactly. Like for example, in this case, it has the kernel access. Here's another thing. There's also a defense evasion. Now this is the one of the most important red flags, that the driver is encrypted, and we have no idea how it was encrypted. In this case, they used the BEC crypt, which means that the encryption was done by a person or a third party processor, not by Windows itself, because Windows doesn't encrypt things with just that thing. So you just have the other regulations like discovery. For example, this means that it is trying to find processes by, so it is trying to discover the registry values, processes by their IDs, gets the information of the system and checks the OS version. That's how you have access to the users and all of these things. Okay. So yeah, okay, this one command and control, which also just tells you. Now the most fun part here, obviously, is the capabilities and behavior. Now in this case, we have the capabilities, so the host interaction, which means that it interacts with the host, so the user, and you can read what exactly this thing does. Right? So it extracts resources through the kernel32 functions, so it has kernel level access, because you see that it extracts resources through the kernel functions, which is not something that regular drivers are supposed to do, especially the third parties. Then you go to the behavior similarity hashes. Most of the time, you're gonna see different things here, and those things are sometimes even scripts or download links and other types of breaches, so that you can analyze the file more thoroughly. Then we have the details. Of course, we already talked about this. You have to check, verify everything yourself. Even if you have a certificate, you have to look at the issuer. But sometimes they will be faked, and those things will not really match. So these ones are regular. These ones are fine. We already know that it is. This just gives you information about how the application was signed and using what signer. So there's that. We also have the relations. And one thing I wanted to show about relations is the graph. We're finally here, basically. In the graph, you see the operation of the temporary assigned system. On some applications, it is normal. For example, applications that are just for games, for example. But no, you don't. If you tamper with the signatures, that is not normal. So that is a red flag. So here you have many things to check. First of all, you notice these icons, and you also notice the visualization. For example, you can visualize it with a tree representation, visualize it with a forest graph representation. So this gives you bundled files, and this gives you the executables, zip files, so everything that it communicates with. What I would do in your place is analyze the executables, because this is how you know. For example, this just revealed to you that it is a kernel driver for system informer, right? It comes from system informer setup.exe. And this one, everything should be from system informer. And then you have the zip files. When you click that, you will see more information about it. So the relations of those files. So for example, go to the dropped files, click on this, and wait for this. So it is going to open other dropped files that this zip file drops. Okay? We have a bad file over here, which is undetected. We have no idea what this is. But the name of it is pulltag.txt. And there's relations. So notice how every time I click on a different file, their relations change. So on this one, for example, relations changed. If I double click on it, for example, this is a DLL file, then it drops you the bundled files. When you click on the bundled files, however, you notice that almost everything links to the same one individual file. That's suspicious. So this is how you would normally decompile and analyze. For example, this also shows you that it uses a .NET DLL, so that is a dependency. This is how you would normally. Yes, exactly. This is very fun. This is even better if the file that you're analyzing is an executable or a renamed file. Let's give that a try. So this is all I want to tell you about drivers. So the way you detect drivers is the signature, structure, and where they come from. And obviously if they are in system32 or not. Basically you can just decompile this. You can go through all of this yourself. You can also just go to the IOC report, which is the individual analysis of this file itself. That just gives you behavior. So you just unlock limitless information about one file. Yes, everything in red is unsigned or flagged as a suspicious file by VirusTotal and other vendors. So you as you can see, you unlock a lot of things. In this case, you also unlocked a lot of links to the virus, links to the system firmware. Right. So this is what a full-scale analysis looks like. And I recommend you guys that you actually review this, analyze it, learn more about this, because it's very useful and very fun. So another thing is that you can basically download this entire, um, you know, all the entire visualization, right? You can export the graph as a CSV, as a PNG image. For example, I just open these, and it's just gonna be an image of the graph itself. If you want to, I will not really tell you to do that because there is no use of this. But yeah, there's an image of a graph. Now let's give you an example of just an executable file being renamed. Okay. So how exactly you would determine that it is a renamed executable? Let's say this is like AnyDesk PNG. This is for demonstration purposes only, so you don't really have to. So first you upload the file that you think is suspicious. In this case, of course, this is gonna tell you exactly what the file is, because we have all of this. But I can go to behavior and go to where's the graph? Where's the graph of this? Where did I find the graph again? Was in details or was it in relations? Yeah, it was in relations. Just go to this and yeah. So here's the file that you have, which is supposedly a PNG file, right? This is the PNG file that we have. Notice how this gives you thousands and thousands of information. This is how you can tell that the file is, first of all, not only faked with a signature, but also renamed a renamed extension. I've never seen anybody do this, by the way, although I've probably never told anybody to do this either, but you get the point. So first of all, what you're looking for are the resources of the file. So the PE means that this file is actually an executable. As you can see here, the PEXE. PE stands for portable executable, as you can see here too. So when you click on this, go to show children list. And this gives you, as you see, the node list. So the exact files that it relates to. So there are two of them. And for example, here you see that this original file actually is a search everything executable. So you see this already. And you found this already, and you have this already. When you click on this, it takes you to the bundled files. For example, when you click on this, it takes you to the bundled files, which means that, okay, so there are 300 files, so okay. This gives you the HTML code, the XML code of it, gives you the execution parents. So this gave you just this one. Dropped files, for example. So let's check what files this drops. So Which one is it? I lost it. Okay, so I think it's these ones. Yeah, okay. There's a lot of files that it drops, basically. And these are the resources. Don't mistake this. These are just resources. By the way, if you want to sort all of this, just do the force graph representation. You're all the way back. So you are able to navigate through all of this information. Although always everything that you have highlighted is already here. You click on this, you see that the file name is search everything, and you can just either go to the files or go to IOC's report, and you found out that these files actually search everything.exe instead of just a PNG file, for example. Right. So, and you also notice that this search everything has nothing detected. This one has thousands of scores, like detections, blah blah. This is a good thing, although the file is obviously safe. This is a good thing because now what you can do is go to the behavior and you can export the rules of these detections. For example, you can find the Yara rules for this. Like when you click more, you can just do, or similar, there's something here that allows you to create Yara rules. I remember it all somewhere. Download artifacts. No, it's not here. Full reports. By the way, these ones are what I was talking about. So this one, for example, gave you the sandbox detection, which, by the way, includes screenshots of the application. So even if you have an application, find this more easy the next time. Yes, not only that, but you just found a renamed extension application. And in this case, you see the screenshots of applications that we just executed. So this PNG file that we just had is search everything, okay? And this detection can be used for files that don't show their GUI when you are connected with AnyDisk, for example, or recording with OBS. So stuff like that, you get the point. The shellcode, right? So this is what shellcode refers to. Shellcode means that in a shelled environment there is a vulnerable code that this driver or an executable drops. It works on stream process. Supposedly, well, I've tested it worked in my case, so I think it should work with any other case. So here's another thing. So I'm looking for the detection rules, for example. Let me see all of them. Right, so these ones are what can give you the detections for example, Yara, if I can find it. No, I can't find it because this one doesn't have a Yara detection yet. But you can basically check those two. Like click on view rule, and this gave you a rule for some other detectable. So that this works on everything basically. For example, when this one view the rule, and this one has this triage reference and as well as this rule, which is the image of the SVC host. You can also go to the triage of this vulnerable driver detection and just do whatever you want basically with this. There's also this one, so you can view the matches. When you click on view matches, what this shows you is that the rules that match the contents of the file. So you can see that this is a part of the file. Okay, so what this tells you is that search everything creates a scheduled task which makes it run on logon. So whenever the user logs on, okay. So that's logical because it actually creates a startup task. If you guys were not aware, like it's here, over here, and I have it enabled for some reason. So yeah, there's that. So you can always analyze those files thoroughly yourself, right? So view the rule, and you have this rule. So yeah, there's that. There's all of that. if you guys have any questions about the kernel level drivers, their detections, and their malware analysis, feel free to ask me them right now. This is a huge information. Yes, it is. This actually teaches you how to analyze malware without paying anybody or anything. So I recommend that you guys do that. However, you can also submit samples to me for me to analyze and create a report for you. So, for example, if you want to analyze something. So, no, it is actually impossible to detect UFI, so the secure boot or BIOS bypasses and strings or scripts through Velociraptor. It is only really possible with volatility, but it is very, very time consuming. So if you are not sure how it works, by the way, we are going to cover that in the digital forensics course. Because, well, if we have the time to, because it is very time consuming and it is very hard to detect, which is why most servers ban for secure boot off, so turned off. So there's also another thing about the UFI bypasses. Um, they don't really always exist. I know a couple of bypasses who have actually developed them. And the way that works is that they still use a USB drive to execute a script on system startup. Yeah, so imagine like installing Windows from a USB drive. Instead, on they log into, so they disable secure boot first of all. They begin the uh the safe startup that allows them to access the terminal before the system starts. And what they do is that they run the VPS script, for example, or a Python script if they have a file in system32 before the system starts. These bypasses are actually possible to detect unless you kinda, dive too deep into the. Well, you will have to try really hard to detect those types of bypasses because most of them don't even log in services because they start before services. So unless the bypasser messed up and left the file on the system or they forgot to so to unplug the USB before the system starts, it's going to be very, very hard to detect those. However, there are theoretical detections. Um, I'm going to be making articles for that. I'm going to be making, presentations for that for the theoretical ways of detecting them. But because I don't have any of those types of bypasses, I can demonstrate myself. So in theory, you will have an idea of what to do if you come across somebody using that. So there's that. Does anybody else have any questions? How long has this been going for? How long has it been? Can be a UFI because, as I said, it's very. Yeah, so I was talking about this error when it happens. But yeah, you would have to use processor to. Oh, it has been exactly 1 hour. That's funny. Okay. Can you repeat the answer? To one. 6 lines. What's a 6 line? Oh, I know what you mean. So with a graph, so the virus total graph. If that's what you're referring to. they will help you get to the heated shellcode of the application. Yes. If that's not what you're referring to, then I have no idea what you're asking. So yeah. Well, for the rest of you, if you guys don't really have any questions, what I recommend you do is that write down the questions that you would want to ask me and send them in the chats so that I implement the answers with the presentations and articles and write-ups that are about to come after this webinar ends. It's probably tomorrow. Probably tomorrow. So yeah, okay. Um, I hope that you guys learned something new about kernel drivers, DLFS, or VirusTotal capabilities. I cannot learn this analysis just by learning. Practice is necessary. If you are asking about VirusTotal, you have to test them yourself. Because as you can see, there is endless information on that. Otherwise, yes, you can just read, you can just, I don't know, I'm gonna write the most useful parts to check. The rest is yours, just malware analysis. So that's it about today's course. I hope that you guys enjoyed the information, maybe learned something, even if you didn't learn anything. I hope that it was still uh, useful. So yeah, there is that. So let me just end. So this one